Hello everyone. In this presentation, our group Yehong, Zhang, and Bowen will talk through the logic of our Python notebook step by step and explain how each part of the code contributes to improving prediction accuracy for house sale prices. Rather than focusing only on the final result, our goal was to build a systematic workflow that moves from data understanding, processing, and model experimentation and toward a final model that generalizes well on the unseen data. And the evaluation metric for this project is RMSE, so minimizing large prediction errors was our primary objective. The notebook begins by loading the training and test datasets using pandas, and at this stage, our purpose of the code is not modeling yet, but understanding the structure of the data. We inspected the dataset shape, previewed records, and identified the target variable sale prices. And the exploratory visualization was then used to examine the distribution of house prices, and we observed the sale price is highly risk-good. This observation directly influenced later modeling decision because skewed target can cause large errors during regression training. Understanding the early allows us to design pre-processing more efficiently. Next, the notebook separates features and target variable. The target variable sale price is transformed using a logarithmic transformation. This is implemented using log1p. The reason for this step is to stabilize variance during training. Without transformation, those expensive houses will dominate the loss function. And the transformation allows the model to earn proportional difference instead of absolute price difference. Later in the notebook, predictions are converted back using exponential transformation so that the RMSE can still be evaluated on the original price scale. After defining the target, the notebook constructs a processing pipeline using column transformer. This is one of the most important design decisions in this code. Instead of manually cleaning data outside the modeling process, pre-processing is embedded directly into the pipeline. This includes handling missing value, encoding categorical variables, and numerical columns are automatically detected, and missing values are filled using median imputation. And the median imputation is chosen because it is robust to extreme values. And those categorical features are filled using the most frequent category and converted into numerical format using one-hot encoding. And embed this step into the pipeline ensures that transformations are applied constantly during cross-validation and final training. More important, it prevents data leakage because validation faults never influence pre-processing learning from those training data.
Before moving to complex models, the notebook evaluates baseline regressors such as ridge regression and decision trees. The purpose of this model is diagnosis rather than performance. Linear models help determine whether relationships are mostly linear. Decision trees introduce a nonlinear learning behavior. Comparing this early model helps confirm that the non-linear interactions are important for predicting housing prices. This justified moving toward ensemble tree-based methods. The next stage evaluates ensemble methods such as random forest and extra trees. These models reduce variance by averaging multiple decision trees trained on random subsets of the data. They are useful as intermediate benchmarks because they are more flexible than single trees while remaining relatively stable. However, results indicated that the boosting methods could potentially provide stronger performance. The notebook then introduced boosting algorithm. Boosting builds trees sequentially, allowing each new tree to focus on correcting mistakes made by previous ones. XGBoost was selected as a strong numerical learner. Light GBM was tested because of its efficiency and leaf-wise tree growth strategy. CatBoost was included because it is particularly effective at handling categorical relationships. Hyperparameters such as learning rate and tree depth were selected conservatively. The intention was not to aggressively minimize training error, but to control overfitting. To evaluate the model reliably, K-fold cross-validation was implemented. Each fold trains on different subsets of data. Out-of-fold predictions were generated. This means every observation received a prediction from a model that didn't train on it. OOF evaluate provides a more realistic estimate of generalization performance compared to a single validation split. This approach is especially important because the hidden test dataset is relatively small. Stable cross-validation results increase confidence that the model will perform consistently. After evaluating individual models, the notebook combines predictions. Different models capture different structure in the data. Weighted average was used to combine XGBoost and CatBoost predictions. Predictions were combined in log space to remain consistent with the transform training data. This ensemble approach was reduced variance and increases robustness compared with relying on a single learner. The notebook also included diagonal visualizations. Predicted versus actual plots helps confirm whether predictions follow expected trends. Residual analysis helps identify systematic bias. Feature importance analysis helps confirm whether the model relies on the meaningful predictors, such as overall qualities and living area. This diagnosis ensures that performance improvements are not accidental. After experimentation and validation comparison, the final model configuration was selected based on stability rather than isolated performance gains. The selected boosting models consistently achieve strong validation RMSE and show balanced bias variance behavior. The final model was retrained using the full training dataset. Predictions for the test dataset were generated using the same pre-processing pipeline. Log predictions were converted back into original cell prices. Finally, results were exported into the submission file required for evaluation. In the summary, the notebook follows a structured progression from data understanding and pre-processing to model experimentation, validation, diagnosis, and final deployment. Each coding decision was designed to prevent data leakage, control overfitting, and improve generalization performance. This systematic workflow allows us to develop a robust regression model suitable for real-world tubular prediction problems. Thank you.